Hello, good morning student. How are you? I hope you all are happy, healthy and fine at home. What did we learn yesterday? Yesterday we learned about the different concept of various terms or the structural effect. I think two structural effect we learned. One is the hydrogen bonding and another one is tautomerism. So these are the structural effect we have discussed yesterday. Today we are going to learn some of the remaining point. What are those points? Let us discuss those points because we are learning the chapter number 1. The name of that chapter is the Fundamentals of Organic Chemistry, and in that, so today's point of discussion is cleavage of bonds. In a chemical reaction, there are as we know that in the organic compound there are covalent bonds are present, so that covalent bond can break two ways, either homolytically or heterolytically. So let us consider one of the simplest example. Suppose let us see here A and B. It is one of the covalent bond, and this bond get cleaved while in a chemical reaction. Let us see another one is a X. Here what you are going to get A in A X plus B, right? If you observe this reaction carefully, what do you see here? What do you observe here? The bond between AB is broken and the new covalent bond is formed between A and X. Means during the course of chemical reaction there is a formation of bond as well as breaking of the bond taking place, and that's why this is known as cleavage of bond, or this type of the breaking or rupture of the covalent bond is known as fission, right? Breaking or rupture of covalent bond is known as fission, right? Fission means breaking, and there are two types of fission or breaking takes place. Number one is known as homolytic fission, right? That is a homolytic fission. In homolytic fission, or it is known as homolysis. What does it mean? Homolytic fission, the covalent bond is breaking. At that moment, the covalent bond is breaking symmetrically. When the covalent bond breaking symmetrically, and as we know that covalent bond is formed due to the sharing of two electron when fission occur or breaking occur symmetrically, the atom, bonded atom, retain its one electron on that atom, and the species obtained is very reactive. That species is known as a free radical. This species is known as a free radical, and that free radicals are highly reactive in nature. Let us see one of the example here. For example, let us consider any example AB. In AB there is a covalent bond. After the homolysis or this type of the reaction generally occur in vapor state. This type of the reaction generally occur in vapor state or in a solution of the solution prepared in a non-polar solvent. Polar and non-polar solvent we already learned in a previous case in the previous lecture. Here this type of the reaction is initiated by, this type of the reaction is initiated, means the reaction are taking place by, these reaction are initiated or taking place under or initiated by light. Initiated by light means sunlight or heat or some other free radical. So this type of the fission or the rupture of the covalent bond is called as fission. Now look at here how it is breaking. This bond is nothing but sharing of two electron. One electron goes on B atom, another electron goes on A atom. I am showing this is a special arrow. This type of the arrow is known as fish hook arrow. On one side only that is shown, these arrows are known as a fish hook arrow. They clearly indicate that they are retaining only as a one electron A, then here B, then that one electron is showing like this, that dot. This dot is nothing but as a, they are the free radical, and these free radicals are highly reactive species. Now let us look at as another example. Suppose there is a chlorine molecule, we know that Cl2, and in Cl, according to as a Lewis dot theory, there is a one bond present between this, and again homolysis, what do you get? Again one electron over here and one electron on another chlorine atom. You are going to get one radical over here, another radical over here. So this type of the radical are known as free radicals. So this type of the free radical are generated mainly in vapor state or in a solution prepared in a non-polar solvent, and these kind of the reaction are initiated by light, heat or some other free radicals. So this is all about the homolytic fission, right? Now let us move on to the second type. The second type is known as, here I am writing here, second type will be the heterolytic. There is a heterolytic fission. Heterolytic fission which is known as heterolysis. heterolysis. And in this fission, the covalent bond is breaking unsymmetrically. Unsymmetrically, as we know that in this fission, in a homolytic fission, the covalent bond are broken symmetrically, means the sharing of electron is equally. But in this heterocyclic, the word itself clearly indicates that the heterolytic fission means what? The covalent bond is broken unsymmetrically, while heterolytic fission, both the electron acquire by the one of the atom and gets negative charge, whereas the other atom is a electron deficient in nature and acquires positive charge. Let us see the simplest example here. Here A and B again. Now in a heterolysis, what is going to happen here? Both the I am showing the arrow. Look at, observe this arrow carefully. What do you see here? This bond is nothing but sharing of 2 electrons. When this arrow I am showing, it means that this B atom taking both the electron and it gets what? It acquires the negative charge. It means this A atom acquires or gets positive charge, and in this case B atom is more electronegative than A, right? Here B atom is more electronegative than A. More electronegative means what? It has the ability to attract more number of electrons toward themselves and gets negative charge. Similarly, for example, suppose A and B, if I am showing the arrow, look at this arrow, and what do you see over here? Here heterolysis process. Now here A gets negative charge, whereas B get positive charge. Here what is going to happen here? A atom is more electronegative than B, and that's why A acquires the negative charge, whereas B acquires the positive charge. And this kind of reaction are initiated by polar solvent. As we know that polar solvent means there is a change in dipole moment, and these reaction are favored by the polar solvent and initiated by acids, bases, oxidizing and reducing agents. So this is known as heterolytic fission. Understood? What do you mean by the homolytic fission and what do you mean by the heterolytic process? Because these are cleavage of bond taking place. There are the two type of the cleavages we have seen now here. Now next point we are going to learn. What is that? Let me clean the board first, and the next point we are going to discuss is the structure and shape of organic molecules. Structure, next point will be structure and shape of organic molecules. Structure and shape of organic molecules. structure and shape of organic molecules. Here, as we know that the process, you might be heard these word or you already familiar with these words, hybridization, right? Hybridization, let me tell you the definition first. What is the definition for hybridization? The process of mixing and recasting of atomic orbital which are different in energy in an isolated atom to form a new set of orbital of equal energy is known as hybridization, and the new orbital obtained is known as hybrid orbital. And there are number of atomic orbital by combining with each other, the atomic orbitals like s orbital, p orbital, d orbital, f orbital. By combining these different orbitals together, we are getting new atomic orbital which is known as a hybrid orbital. And there are when we are getting as a hybrid orbital, number of remember one rule is there, number of atomic orbital participate in the hybridization, number of new hybrid orbital are formed, and when new hybrid orbital form, they have maximum symmetry and there is a definite direction, means orientation in the space. And by using different type of the atomic orbital, there are number of hybridizations are possible. But as far as F.Y.B.Sc is concerned, by using only s and p orbital, we are going to learn, because it is useful as far as organic chemist point of view is concerned, and therefore we are going to learn here only using s and p orbital, using s and p orbital, yes. By using s and p orbital, there are different hybridization. Now by using s and p orbital, how many hybridizations you are going to get? Hybridizations, there are, by combining s and p atomic orbital, generally we are getting number one is a Sp3 hybridization. Sp3 hybridization, and which has definite geometry, that is a regular tetrahedral geometry. And second possibility of hybridization, the mix s orbital and 2p orbital, that is known as sp2 hybridization, sp2 hybridization, which is known as trigonal planar geometry, and B you can call it. Then C, which is one s orbital and one p orbital participate, we are getting sp hybridization, sp hybridization, and which is known as diagonal or what we can call it as a linear shape, diagonal or linear shape, trigonal planar shape. So these type of the hybridizations are possible, and these hybridizations are very, very useful as far as a chemist point of view is concerned, because there are three type of the carbon present in the organic compound. Suppose your organic compound containing as a carbon-carbon single bond, that carbon is showing as a sp3 hybridization. If the carbon-carbon double bonds are there, it shows as sp2 hybridization. If carbon-carbon triple bonds are there, that shows as a sp hybridization. And so these type of the hybridization, it is a hypothetical process, but it is a very useful for the organic chemist. And therefore today we are going to learn the first one, which is known as a Sp3 hybridization, that is a tetrahedral geometry, right? Now here, while writing as a Sp3 hybridization, first molecule, so 5 mark question or 4 mark question may appear here. What is hybridization? Discuss the formation of methane molecule with suitable example, or let us see here what is hybridization. Just here the first one is a formation of methane molecule we are going to learn. Formation of methane molecule. Formation of methane molecule, and as we know that methane molecule. Formation of methane molecule, and as we know that methane molecule is a this one CH4. Now this CH4, as we know that methane molecule is a CH4, one of the carbon atom attached 4 hydrogen atom. Now while showing as a Sp3 hybridization, according to our definition, what is the definition? The process of mixing and recasting of different atomic orbital when they overlap to form a new atomic orbital which is equal in energy is known as a hybridization, and the new orbital form is known as a hybrid orbital. First of all, let us see which is a central metal atom present in this molecule. Always remember, those are having as a higher atomic number is known as a central metal atom, and the whatever less number of atomic the smaller number of atomic number attached to that carbon atom. Generally, as far as organic chemistry is concerned, always remember carbon is a central metal atom and other means hydrogen atom is a attached to it, and therefore, and as we know that carbon atom has a atomic number is a 6. Everybody knows that. It is present in the second row of the long form of the periodic table, right? Okay. Now, how do you might be knowing how to write as an electronic configuration, and we generally writing as an electronic configuration on the basis of above principle, right? And by knowing that energy level diagram, we can able to write the electronic configuration of any element in the long form of the periodic table. As we know that till today there are 118 elements are present in the modern periodic table. So let us see one of that carbon atom is there. So electronic configuration, as we know that 1s2, then 2s2 and 2p2, right? 6 carbon atom are there. This is atomic number. Atomic number is nothing but as a number of electrons present in that carbon atom. And now this s orbital has a capacity to accommodate how many electron? It can accommodate only as a 2 electron. As we know that these are the different atomic orbital: s orbital, p orbital, d orbital and the f orbital. Do you know the capacities of accommodation of these these orbital? S orbital can accommodate 2 electron, p orbital can accommodate 6 electron, d orbital can accommodate 10 electron, and f orbital can accommodate 14 electron. These are the capacities. And as we know, do you know the subcells of that atomic orbital? S orbital are spherical in shape, p orbital are dumbbell in shape, d orbital there are the 5 subcell, f orbital there are the 14 subcell. But we are not going to discuss this one, only to remember s orbital and according to their history, S stand for the sharp, P for principal, D for diffuse, and F for the fundamental. So these are the atomic orbital and their capacities to accommodate the number of electrons. Now once you write this electronic configuration by following the above principle, what do you see here? This is a 1s orbital which is present nearest the nucleus. It is completely filled, therefore it does not taking part in the formation of the bond. What is remaining? These electrons are known as a outer valence electron, and outer valence, number of outer valence electron, number of bond they can form. Now let us look at as a electronic configuration. Now this one, as we know that this is a 2s orbital and these 3 subcells are there. S orbital are different in shape, these p orbital are again different in shape, different in energy, everything is a different over there. Now the electrons are filled according to as a Hund's rule of maximum multiplicity. So there are in s orbital there are the 2 electron, and these 2 electron I am showing there is a opposite spins are there, one is above, one is below, and therefore this completely filled, that become as a stable. Now 2 electrons are there, 2 electron we can show according to as a Hund's rule of maximum multiplicity. This subcell, this is known as a 2px orbital, this second one is known as a 2py orbital, third one is known as a 2pz orbital. These are the 3 atomic orbital of that p orbital 3. And now while writing as a what we can call it as in a p orbital, there are the 3 subcells are there, right? So some of the student might show the electronic they can feel 1 electron over here, 1 may be here, 1 electron here, 1 may be here, 1 electron are this. These are the completely wrong, because this the Hund's rule tells that no electron will enter period in a subcell until the subcell contain as a 1 electron. So that should be shown as a this type. This type is not the way of filling that electron. So remember always here. Now this is a ground state electronic configuration of this carbon atom. Now if you look at, there are only 2 unpaired electron, but actually carbon atom has a 4 unpaired electron. Number of unpaired electron, number of bonds are formed. Here if you look at, there is a 4 carbon bonds are there with that hydrogen atom, and therefore when such a type of the molecule is formed, the central atom goes in the excited state, and this when it goes in the excited state, what is happening, why it goes in the excited state, where does the energy come from? Look at here, one of the electron from 2s orbital goes into the p orbital, means here 2s orbital containing only 1 electron and 2 is already there, and that this 1 electron goes here. So if you look at this one, there are the 4 unpaired electron, means 1s orbital and 3p orbital, they combine together, overlap or hybridize, it is known as a new atomic orbital. By mixing 1 2s orbital and 3p orbital together, we are getting a new orbital. Number of atomic orbital count here, 1 2 3 4. So there are 4 sp3 orbitals are obtained, and this is known as a sp3 hybridization. sp3 hybridization, and as we know that sp3 hybridization has a tetrahedral geometry. Understood this one? Tetrahedral geometry. Now as we know that s orbital are spherical in shape, you can show this 2s orbital, and as we know that this is the x axis, this is the y axis, and this is a z axis. This is a 2s orbital. Remember, this is a one atomic orbital combined with p orbital, and as we know that the p orbital has a dumbbell in shape. This is the x axis, and how do you draw that dumbbell shape? You can show as this type of the dumbbell shape. This is known as a 2p x orbital, and then 2p y orbital. 2p y orbital you can show like this, slightly inclined. So this is a y axis, and that you can show like this. This is a 2p y orbital, right? Or here you can write y orbital, and this is a 2p y orbital, and plus what is that? Then z orbital. Z orbital we can show like this. This is a z orbital, z axis. This is a 2p z orbital. Look at, there are the 4 different atomic orbital, 2s, 2px, 2py and 2pz. When they overlap, what do you get? After overlapping, here overlap, or you can call it as a hybridize. What do you get? There are number of atomic orbital is equal to number of hybrid orbital. So here you are going to get this type of the one orbital over here, then another one, this one, another orbital like this, and fourth one is this. This is called a sp3 hybrid orbital. This is a sp3 hybrid orbital. When there are these 4 sp3 hybrid orbital, only one sp3 orbital are like this. One lobe is a large and one is a very small. This is known as sp3. The maximum electron density get concentrated toward the one side, and other is this. This is a 1s. These are the 4 orbital of sp3 new hybrid orbital, and it has tetrahedral in nature, tetrahedral geometry, and the bond angle found in the tetrahedral geometry is 109.5 degree, right? 109.5 degree. That is a definite angle present in a tetrahedral geometry. That is a characteristic or important feature of that. Now these 4 sp3 hybrid orbital overlap with 4 1s atomic orbital. 1s atomic orbital, as we know that hydrogen atom having as atomic number 1 only, that is a 1s1 electronic configuration, and there only one electron is present, unpaired electron. So these 4 unpaired electron get combined with 4 sp3 hybrid orbital, and we are going to get 4 CH sigma bond, and these sigma bond are formed due to the coaxial overlapping. Coaxial overlapping, and coaxially overlapping means maximum number of electron density concentrate between the 2 atoms, and that type of the bond is called as a sigma bond, and that sigma bond is a very stable as compared to the pi bond. Pi bond in the next time we are going to see, but here the 4 atomic orbital combined with this 1s orbital of hydrogen atom. As we know that s orbital having as again is a spherical in shape like this, x, y and z, and what you are going to get? You are going to get here the structure again is like this. Look at this structure carefully. This is the sp3 hybrid orbital, and this s orbital combine here. This is a hydrogen atom, and this is forming as a sigma bond. Here another hydrogen atom which is forming as a sigma bond over here, another hydrogen bond which is forming as a sigma bond here, and another hydrogen atom which is forming as a sigma bond here, and the overlapping, how the overlapping one s orbital and one sp3 atomic orbital get overlap, we are getting as a coaxially, we are getting as a formation of the sigma bond. This is the representation of formation of the methane molecule. Now this methane molecule, how to show this methane molecule? There is a central metal atoms are there. This is a central metal atom. There are 4 hydrogen atom. I am showing here hydrogen atom. They can attach like this. This is a hydrogen atom over there, and this is a tetrahedral geometry. This is a tetrahedral geometry, right? So this is the structure of tetrahedral geometry, that carbon, and generally we are showing as a this carbon like this, right? So this is the representation or the formation of the methane molecule. I think with this we have completed all the point of this remaining hybridization, sp2 hybridization and the sp hybridization, as well as formation of the methane molecule. We will discuss in the next lecture. Let us stop today here. Thank you. Have a nice day.